a little bit about things that don't quite conform to the octet rule. These are non-conformers. The bottom, what is it, 6 on your packet are all non-conformers. You can't do the Gooch math. You can't count octet, count valence, count shared, and get a correct structure for these. So there are 2 different ways that something can be a non-conformer, and we'll talk about the least common first, and we'll talk about it with, well, let's use boron trifluoride, okay, BF3. So you know that fluorine has got a pretty, well, what do you know about fluorine's electronegativity? Very high electronegativity. Fluorine loves electrons. Fluorine tends to pull electrons away from other atoms. That's good to know going in. Boron, if you remember from your notes, is an exception to the octet rule. Sometimes boron is actually, like boron is just kind of an underachiever. It's just okay with 6 electrons. It doesn't always reach octet in compounds, and it seems to be satisfied with that. So there are a couple different options. Knowing going in that this is not going to meet octet, so it's listed as a non-conformer. You know, we could do the strategy of, well, let's tie it all together with single bonds and put all the valence electrons that it started with on it and just see what that looks like. Okay, so we've got boron in the center. How many valence electrons does boron have to start with? 3. So at this point, what boron has done, if we assume this is the correct structure, is, you know, boron, which was looking like that, has kind of done that keyhole fit and is sharing with fluorine. And that seems easy enough. It's just sort of linked every place that fluorine had to share a single electron, every place boron had to share a single electron. This is not a charged molecule. We can't add electrons. Is there, you know, could there be an unshared pair on boron? No. It's unlikely that you would see that. Could you have, well, you know, what if 2 of these sort of move over and form a double bond? And then we have, well, we would show it like this. Is that possible? Well, then boron's happy and fluorine's more or less happy. There are some concepts that are a little bit beyond what we get into here. There are concepts of what are called formal charge. And formal charge is comparing the actual number of electrons surrounding a nucleus to the number of protons in that nucleus. Like I said, we don't do it here. If you take a good college, you wouldn't even do it in a Gen Chem 1. You would do it in a higher level inorganic chemistry. But when you look at formal charge, you have to think about what's really electronegative. And something that's really electronegative will tend to have a negative formal charge. It will tend to have more electrons surrounding it than protons in the nucleus, because they love electrons. This structure would give boron a formal charge, a negative formal charge. Boron would have extra electrons, and fluorine would be giving up electrons. Do you think fluorine's likely to give up electrons? No. You're going to have to pry them out of its cold, dead hands. It's not going to happen. So it's unlikely, and again, this is kind of beyond what we do, but I just want to have the discussion. It's unlikely this is the actual structure. So if you remember back when we talked initially about how we figure out molecular geometry and how we figure out molecular structure, it is repeated model making, it is repeated experimentation, it's actual testing of substances. And so, you know, somebody somewhere wrote their master's thesis on the structure of boron trifluoride, I would bet. Because it's one of these things where it's not an easy, obvious solution to structure. So somebody did formal charge work, somebody did testing of boron trifluoride and looked at the actual length of the bonds. What would that have to do with it? What can we tell from the length of the bonds? if they are single or double or triple. Because remember that as you double up, it starts to pull closer. So double bonds tend to be shorter than single bonds. Triple bonds tend to be shorter than double bonds. So what has actually been found, interestingly enough, and I don't, you know, we can go with this and we know the sort of like little thing we've got sitting on the back shelf that says, yeah, boron's often happy with just 6. Does boron have 6 here? Yeah. So it's okay. What I find interesting, and this is totally like above what you need to know, but it's, for those of you going on in chemistry, you may find it interesting. I read an article about this particular compound, and they were saying that, you know, that double bond structure that I showed, it's actually, so experimentally, when they look at the bond length in boron trifluoride, what they find is that the bonds are not as short as you would expect a double bond to be, but they're a little bit shorter than you would expect a single bond to be. And the hypothesis based on that, and based on a lot of math that we're not going to go into here about formal charge, is that it's probable that this compound actually exhibits resonance between all single bonds and between having one double bond. And what we used to think is compounds like sort of flipped back and forth between two states. And actually there's a third possibility. There is a third possibility for this. Let me get the third possibility on here. So, you know, we've got option 1, boron's just an underachiever. It's just okay having less than 8. And it doesn't make a big fuss. It's a good molecule. It's a little quiet molecule. Another option that was mentioned in the article I read was that in fact what happens is that fluorine is so electronegative, it actually steals that other electron off of boron, and then you have, well, what would this be? I didn't leave myself enough space. And then you have something like this, where it behaves sort of as though this is a polyatomic ion bonded to a fluorine ion. So we got 3 possible options for structure, and they're all weird, and none of them satisfy the octet rule. What this article was saying is that it is quite, so this is, other analytical work done on boron trifluoride points to it having a pretty high ionic character. There's a fairly good difference between the electronegativities of boron and fluorine. And what this article was saying is that it's quite possible that boron sort of exhibits resonance between all 3 of these states. Whoops. That it sort of goes back and forth between these 3 conditions. That's weird. It's cool. Now, could you figure that out with pencil and paper? And no, you couldn't. That's way above what we do here. But it's interesting to know that, and to know that molecules do some things that we don't necessarily expect them to do. I don't expect you to, you know, remember or know that or draw resonance for this. I expect you to go with that. Go with the fact that boron is generally satisfied with 6 electrons, and we can do a reasonable structure here. All the fluorines are happy, and, you know, Marcia. All anybody cares about is that fluorine's happy because fluorine's such an electron hog. But it's, you know, what I find fascinating is there is more to it. And what we have found out about resonance in, I guess this was known 20 years ago. It's the kind of thing that we often don't talk about at the high school level, but you will talk about, or it will be assumed at some point that you have caught on to at the college level. When we talk about something that has resonance, it's not as simple as that double bond moving. That double bond, okay, so what we used to think was that you know, the way it's kind of generally taught at the lower level chemistry is that double bond moves, and it's here, then it's here, then it's here. And actually, what's understood now is that it kind of, each of those exists as like 1.3 bonds, like a 1.3 bond. Like it's never quite a single, it's never quite a double, it exists in this sort of in-between space. I mean, think about it, electrons are in constant motion. They're the kind of thing that you can't sit still, we can't even measure where they are and how fast they're moving. So it kind of makes sense that it's not as simple as we make it out to be. But, okay, so that's enough about weird oh, no, wait, we got to talk about expanded valence. Silly Moser. Okay, so the opposite situation of something like boron, where boron's an underachiever, it's happy with less than 6, is something really weird. Let's look at sulfur hexafluoride, Sf6. I'm telling you right off the top, it is a non-conformer. You can't do gooch math and figure this one out. Now, what's going to be central? Sulfur. It's the odd man out. You know, we always kind of intuitively know that if there's one of something and a bunch of something else, the singleton's in the middle. Okay, so what does sulfur start off looking like? Well, it's in the same family as oxygen, starts off looking like that. 2 sites for attachment. Cool. We see like sulfur dioxide, it attaches to 2 oxygens. Oh wait, sulfur, hold on. Okay, so if you have 6 fluorines to tie to this thing, how are you going to do it? It's like trying to plug 6 things into a 2-prong outlet. How are you going to do that? Does this work? It would form what?
Would they be able to form bonds within themselves?
What, like fluorine to fluorine? Nope, fluorine's only got one place to attach. I mean, fluorine's pretty open and shut, if you think about it. Because fluorine, 1, 2, 3, 4, 5, 6, and then 7. So fluorine really doesn't have a whole lot of options. It can only bond once. All your halogens can only bond one time. So, I mean, the first 2 were easy. Like I can see the first 2 easily. I have to move that down a little bit. I get that. And I get shoving one on the other side. But then what do? You got 4 fluorines left to shove into, like I said, you're plugging 2 things into a double outlet. Now here, let me give you 4 more cords. Make it work. So, this is called expanded valence. Once again, let's go back to this question. What do you know about fluorine? Highest electronegativity we know of. Loves electrons. Greedy for electrons. So, what happens in this case, and a few other cases, is we get this situation. 1, 2, 3, 4, 5, 6. Fluorine, 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 fluorine. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It looks like a porcupine, doesn't it? It's kind of crazy. Let's count octet. So fluorine started off with 6 valence electrons, and sulfur started off with 6 valence electrons. Each fluorine started off with 7. So, we can't do octet, but we can do 6 times 1, 7 times 6. So 6 plus 42. So we have to have 48 electrons represented. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46. Did I do my math right? 7 times 6 is 42. Okay, did I count valence pairs right? It seems to me this should work out. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, oh, 48. We have all the valence electrons we started with. I missed one. We haven't lost any electrons, we haven't gained any electrons, and this is a non-charged molecule, so that would be what we would expect. Looks much worse now. Let's get rid of my little orange hash marks. What happened here? What happened here? Well, if we remember that sulfur started off looking like this. Fluorine is so powerfully attracted to electrons that it can actually sort of break up these pairs and make them act as though they are single, unbound electrons free for bonding. And those move out away from the sulfur. They break up those little happy couples and create bonds. They share those with the fluorine. And because of the fact that fluorine is so electronegative, if we think about this in terms of the electron cloud, I mean, right now it looks as though sulfur is surrounded by 12 valence electrons. And that would be way overload. That's more than an element like sulfur can handle. But what's really happening is that fluorine is so electronegative that the effects of that, if we remember there's that sort of electron cloud blanket, I'll draw it as sort of a little flower here, what happens is that the fluorine atoms pull the covers off of sulfur. So even though sulfur is surrounded by more than 8 electrons, it doesn't feel that because fluorine's basically carrying the load. Have you ever lifted something really heavy with somebody really strong? My cousin, I joke about him being a bear. He's just, and his dad was the same way. He's a huge guy, and he is just stronger than you would expect any human could be. He's just this big farm guy, and he's just crazy strong. I mean, like, he can lift an engine block and not think about it and not grunt. Like, he lifts stuff, and other people go, oh, it must not be that heavy, and then they go, you know. And I have lifted stuff with my cousin, and I'm thinking, oh, this isn't so bad. I'm really strong. No, he's carrying 75% of the load. I'm not feeling the load because he's carrying way more than his fair share. That's what's happening here. Fluorine is carrying way more than its fair share of the electron cloud. So sulfur doesn't feel like it's crowded by electrons. Does that make sense? So you're going to see anytime something's bonding with a halogen, because halogens tend to be what? Very electronegative. Anytime you got something bonding with a halogen, you can have these unusual structures where the central atom appears to be surrounded by more electrons than are reasonable, but it's actually not. And it's called expanded valence. Most of your non-conformers are going to be expanded valence type issues. There is one on there that is so weird and so tricky. The first time I used this lab, it was the first year I taught chemistry, Mr. Voorhees was still teaching chemistry. He was using the same lab, and he and I both ended up having to like Google solutions for this arrangement because we're like, there's no way to make this work. You can't make this work. This is crazy. It works. I'll leave you guys to figure out which one that is. So we'll stop there, and I'll let you finish those, and then in the second period we'll talk a little bit about hybridization.